This video is a supplementary learning material to accompany the self-learning module titled Molecular Polarity, together with Teacher Jackie and Teacher Den.
Have you ever wondered how a dishwashing liquid works in cleaning oily or greasy pans? Perhaps those of you who have experienced washing oily dishes or pans could relate to this. Did you also know that polarity plays an important role in the cleaning action of soap? How? Let me help you find the answer. The chemical structure of soap includes both polar and nonpolar parts. These parts allow the soap molecules to interact with both oil and water. And let's get to know more about this. The main cleaning ingredient of soap and dishwashing liquid is usually sodium lauryl sulfate, which is a polar part and a nonpolar part. The sulfate group is polar, while the carbon chain on the other end is nonpolar. When soap is added to water, soap molecules spontaneously arrange themselves into spherical clusters and form micelles. Note that even if oil or nonpolar substances are not present, formation of micelles occurs spontaneously when soap is in water. The water-loving or hydrophilic polar heads of the micelle structure interact with water. On the other hand, its water-hating or hydrophobic nonpolar tails interact with oil. With this structure, soap micelles can trap oil and dirt and at the same time can be washed away with water. And that is how polarity plays a huge role in the cleaning action of soap. But how do we determine the molecular polarity? How do polar and nonpolar structures differ? Well, these are what we are going to find out. So this video presentation focuses on determining the molecular polarity using a charged plastic ruler. At the end of this video, you must be able to do three things. First, determine the polarity of the bonds in a molecule based on the electronegativity difference of the atoms. Second, classify the sample liquids as polar or nonpolar based on their behavior toward the charged plastic ruler. And lastly, relate the polarity of the molecule with the polarity of its bonds. This video has two main sections. The first section is a demonstration of the activity, which I am going to present. The second section is the post-activity discussion, which will be presented by Teacher Den. Are you ready? Let's keep the video rolling. I'm going to present to you how to perform the activity using materials commonly found around you, even in your home. Through this activity, you will be able to answer the main question: how is molecular polarity determined using a charged ruler? First, we need to prepare the materials that you need for the activity. As we said, these are materials that you can commonly find in your home. For example, 50 ml tap water, 50 ml 70% ethyl alcohol or ethanol for short, 50 ml baby oil, and 50 ml cooking oil. These are our 4 liquid samples. Bear in mind that the brands do not matter. You may use any brand that is available to you. Aside from the 4 liquid samples, we also need PET bottles. Since we have 4 liquid samples, we also need 4 PET bottles. Take note that for the cap of the PET bottles, we punched a hole in it. So each cap has a pin hole. What else? You also need basins. Now, we have 4 liquid samples. If you have lots of basins, you can use 4 basins. But if you have limited basins, you can just use 1. Just make sure that you dry them, clean them before using it in another sample. You also need a plastic ruler. This is very important because that is the one that we are going to charge in a bit. and just to make sure that we have something to clean up our mess or dry up some of our materials, we also need some tissue paper, 8 sheets maybe. As we also need labeling materials. So, do you all have the materials? Don't worry, if you do not have all of them, just watch our video and perhaps you can just view and observe the behavior of our liquid samples through this video. Okay, all set? Let's go! In this activity, you will determine the molecular polarity of liquids based on their observed behavior towards a charged plastic ruler. Before, during, and after doing the activity, it is important for you to follow the safety precautions. Here are the safety precautions for this activity. First, use clean bottle containers for the liquid samples. Second, label all the bottle containers and basins to avoid mixing the liquid samples. Third, never taste the liquid samples. Fourth, discard all the waste liquids properly. Lastly, keep your work area clean before, during, and after the activity. Let me guide you in this activity step by step. The first liquid sample that we are going to use is water. Now, for the procedure, the first step is always charging the ruler. How do we do this? How do we charge a ruler? We can do this by strongly rubbing the face of the plastic ruler against our hair for about 20 seconds. Just make sure that your hair is not wet or doesn't have gel or oil. Also, insert just enough force and be careful not to hurt yourself. Now, how do we know if we have successfully charged the ruler? Well, we can do this by bringing the rubbed area of the plastic ruler near small pieces of paper, just like what you're seeing now. If the small pieces of paper get attracted to the face of the plastic ruler, then congratulations, we have successfully charged our ruler. Next, prepare a clean, small labeled basin. Then the PET bottle containing water, turn it upside down and squeeze it to produce a steady, fine stream of water. Can you see the fine stream of water? Make sure to catch all that water dripping into the clean, labeled basin. Label the basins with the name of the liquid sample. The liquid samples can be reused at a later time or in case the PET bottle needs to be refilled. A word of caution. Yes, you have to bring that rubbed area of the plastic ruler near the fine stream of water, but make sure that the plastic ruler never touches that fine stream of water as it flows down from the bottle. And that holds true for any of our 4 liquid samples. Now, if that happens, oh no. So, let's continue doing this properly. As we said, the first step is to charge the ruler. We charge it by rubbing it against our hair for about 20 seconds. Immediately after, bring it close to the fine stream of water, but make sure that the plastic ruler does not touch the water. Now, observe what happens to the fine stream of water as the plastic ruler is brought near to it. Based on your observation, what could be the polarity of water? For our second liquid sample, we will be using 70% ethyl alcohol or ethanol. So we will try to find out the molecular polarity of ethanol using the same steps we did for water. Note that 70% ethyl alcohol in rubbing alcohol is used in this activity. So before we start, make sure that you have a complete setup. You have your PET bottle containing the 70% ethanol. Make sure the PET bottle is covered and that the cap has a pinhole in it. You have your basin. You can label it with ethanol this time, but make sure it's dry and clean. especially if the basin that you will be using is the same basin that you used for water. And of course, you also have your plastic ruler. Okay, when everything is complete, you may now start charging your ruler. Again, we charge it by rubbing it against our hair for about 20 seconds. Then, the PET bottle containing the 70% ethanol, turn it upside down, squeeze it to produce that fine, steady stream of ethanol. Because once your ruler is charged, you have to immediately bring it close to that fine stream of ethanol. Now, try to observe what happens to the fine stream of ethanol as you have brought the plastic ruler close to it. Based on that observation, what do you think is the molecular polarity of ethanol? Now, on to our third liquid sample. This time, we will be using cooking oil. But we will be doing the steps as we did for water and ethanol. So make sure your setup is complete, like you have your basin to catch that dripping cooking oil this time. You have your PET bottle with cover, and the cover has a pinhole in it. And the cooking oil must be inside the bottle already. And the plastic ruler. Now, the first step is to make sure that you charge the plastic ruler. And we do this by rubbing it against our dry hair for about 20 seconds. Now, the PET bottle containing the cooking oil, turn it upside down, squeeze it to produce that steady fine stream of cooking oil. Because immediately after you have charged the ruler, you have to bring it close to the fine stream of cooking oil. And then, as you bring it closer, observe what happens to that fine stream of cooking oil. Based on your observation, what could be the polarity of cooking oil?
What happened to the stream of cooking oil as a charged plastic ruler is brought closer to it? Did you observe the same movement of the cooking oil as that in the movement of the water and ethanol? Now again, basing from your observations, what could be the polarity of cooking oil?
Yay! Now on our fourth and last liquid sample, baby oil this time. So we will be using the same steps we did for water, ethanol, and cooking oil. And again, before starting everything, make sure that your setup is complete. Like you have your basin that will catch the dripping baby oil this time. You have your PET bottle that contains the baby oil. Make sure it is covered and that the cover has a pinhole in it. And your plastic ruler. Everything is set? Now, let's start doing it to our fourth sample. Let's charge the ruler now by rubbing it against our hair for about 20 seconds. And then the PET bottle containing the baby oil, turn it upside down, squeeze it to produce a fine stream of baby oil. And then, immediately after charging the ruler, bring again that plastic ruler near the fine stream of baby oil. Then, observe what happens to that fine stream of baby oil as you bring that plastic ruler close to it. Again, based on your observation, what could be the molecular polarity of baby oil?
Did you observe the same movement of the baby oil as that in the movement of the cooking oil? How about with the movement of ethanol and water? Again, based on your observation, what could be the polarity of baby oil?
That's it! We are all done determining the molecular polarity of our 4 liquid samples using a charged plastic ruler. Can you think of other liquids that would exhibit the same polarity as that of our four liquid samples? Well, we hope so. Well, now that we are all done with the activity, it's time for you to learn the concepts and ideas behind it. Here is Teacher Den to guide you in the post-activity discussion.
How are you? I am Teacher Den. This time, let us discuss the results of your activity and the key concepts involved in it. In the activity that you perform, you determine the polarity of substances. That is, whether a substance is polar or non-polar. But, what do you think is the difference between a polar molecule and a non-polar molecule?
Now, when we say that a molecule is polar, it has an atom at one end of the bond that is slightly negative and an atom at another end of the bond that is slightly positive. This is due to the difference in the electronegativity values of the atoms comprising the molecule. So, what do you mean by that? This means that in a polar molecule, one element, the electronegative element, pulls the shared electrons more than the other elements, which results in an equal sharing of electrons between elements. This gives the more electronegative element a partially negative charge, and the more electropositive element a partially positive charge. What do you think this will create? This unequal sharing of electrons will create a net dipole moment, which is a measure of the charge separation within a molecule.
To further visualize these descriptions of a polar molecule, let us take a closer look. Hydrogen chloride is an example of a polar substance. Are you familiar with this substance? What can you say about the electronegativity of its atoms, hydrogen and chlorine? The electronegativity value of hydrogen atom is 2.1 and the electronegativity value of chlorine atom is 3.0. This shows that chlorine is more electronegative than hydrogen. Thus, chlorine pulls the shared electrons toward itself. This gives chlorine atoms a partially negative charge and hydrogen atoms a partially positive charge. What else? This also results in a net dipole moment represented by a one arrow pointing to the more electronegative chlorine atom. Let us note that by convention, the tail of the arrow is crossed to indicate where the partially positive end is located. In our example, the tail is crossed at the H end. This means that H is the partially positive atom.
At this point, you have learned about a polar molecule. Now, let us proceed to a non-polar substance. Can you guess how it is different from a polar substance?
This is a chlorine molecule. This is an example of a non-polar substance. Unlike polar substances, non-polar substances do not have net dipole moments. For example, the chlorine molecule. Its two chlorine atoms have the same electronegativities and have equal sharing of electrons. Thus, the chlorine molecule has no net dipole moment and is nonpolar.
Now, let us proceed to the second part of your activity, where you identified the molecular polarity based on the observed behavior of the liquid towards a charge ruler. So, when you put the rub area of the plastic ruler near the fine stream of each of the four liquids, what did you observe? I would like to think that you observe some liquids move towards the charge ruler while others did not. Let us confirm this observation with what happened in the activity. The sample liquids here are water and ethanol. You notice that the stream of water and ethanol move towards the charge ruler. Did you observe the same in your activity? How about the other liquids such as cooking oil and baby oil? Let us see how they behave toward a charge ruler. You saw that there are no observed changes in the movement of cooking oil and baby oil when they are placed near the rub ruler. Why do you think these cases happen? Do you have any inferences obtained from the activity? One inference is that water and ethanol are both polar liquids. They move toward the charge ruler because of their partial charges. The other inference is cooking oil and baby oil are non-polar liquids with no net dipole moment. Thus, they did not move toward the charge ruler.
Now, what must be the polarity of the bonds that are present in the molecules that make up these liquids?
Let us look first the bonds in water and in ethanol, two molecules that are both polar. Based on the difference in the electronegativity values of its atoms, we can tell that water is composed of polar oxygen-hydrogen bonds.
On the other hand, based on the difference in the electronegativity values of its atoms, we can tell that ethanol is composed of polar bonds. Those are carbon-oxygen bond and oxygen-hydrogen bond. And non-polar bonds, those are carbon-carbon bond and carbon-hydrogen bond. Water and ethanol are both polar molecules. But as you have seen, there are polar molecules which may contain non-polar bonds such as ethanol.
Now, how about the bonds of cooking oil and baby oil?
These two oils are both non-polar liquids. They are made of non-polar molecules. Palmitic acid in cooking oil has polar and non-polar bonds, while octadecane in baby oil has non-polar bonds only. In this case, you saw that there are also non-polar molecules which may contain polar bonds, such as palmitic acid.
Now, let us focus our attention on this question.
One way to determine the molecular polarity based on structure is by examining the polarity of each bond.
It is important for you to remember that when the bonds within a molecule are polar, it does not automatically mean that the entire molecule is polar. The molecular polarity is the same as bond polarity, only if the molecule is made up of two atoms. In this case, the polarity of the bonds between these two atoms will also be the polarity of the entire molecule.
Let us visualize that explanation by revisiting the molecular structures of hydrogen chloride and chlorine, together with the difference in electronegativity of their bonded atoms. What do you notice? You can see that each molecule is made up of only two atoms. The hydrogen chloride molecule is made up of a polar bond. Thus, the molecule is polar. On the other hand, the chlorine molecule is made up of a non-polar bond. Thus, the molecule is non-polar.
Now, aside from examining the bond polarity in its structure, can you think of another way to determine the polarity of a molecule?
If you observe that the atoms are symmetrically arranged in the molecule, the dipole moments would cancel out.
And so, the molecule is non-polar.
But take note that this technique is useful only for simple molecules, those with just one central atom to which all other atoms are attached. For example, carbon dioxide, which has one central atom, carbon. Xenon difluoride also has one central atom, xenon. And xenon tetrafluoride, also xenon as the central atom.
For molecules made of three or more atoms, the arrangement of the atoms and the bonds relative to one another is important in determining the polarity of molecules.
That can be illustrated in this example. Let us take a look at this structure of carbon dioxide. Based on this illustration, you will notice that the elements are arranged symmetrically. The dipole moment of the two carbon-oxygen bonds are equal and pointing towards opposite directions, so they cancel one another. Since the molecule has zero net dipole moment, the carbon dioxide is a non-polar molecule.
In our explanations, you have learned about symmetrical molecules. What can you say about these molecules? Symmetrical molecules are those that contain the same peripheral atoms and at the same time do not contain a lone pair in the central atom. One example of these molecules is carbon dioxide. However, there are exceptions to this description of symmetrical molecules. Some examples of these exceptions are some linear and square planar molecules like xenon difluoride and xenon tetrafluoride. These molecules have lone pairs in their central atoms, but they are still considered symmetrical molecules.
To visualize that, let us study these structures of linear xenon difluoride and square planar xenon tetrafluoride. What can you say about their bonds? You will notice here that in both linear and square planar molecules, all xenon fluoride bonds are directly opposite of another xenon fluoride bond. Because of this, the dipole moments of all the bonds cancel out, which makes xenon difluoride and xenon tetrafluoride molecules nonpolar, despite having lone pairs in the central atom. How about if the molecule is asymmetrical? What can you say about its polarity?
If the molecule is asymmetrical, the bonds may have dipole moments that could not cancel each other out, thus making them polar.
Let us illustrate our explanation in this example of an asymmetrical molecule. You can see here the structure of cyanogen fluoride with unequal dipole moments of its bonds, thus they cannot cancel each other. This makes cyanogen fluoride a polar molecule. Let us take a look at another example of an asymmetrical molecule. This is water. What do you notice here? In this illustration, you will notice that even though water is made up of the same peripheral atoms in the form of hydrogen atoms, the two lone pairs of electrons on its oxygen central atom made the molecular group geometry of the water molecule bent. Based on this structure, the water molecule is asymmetrical, which makes it polar.
There you go! That would be all for our post-activity discussion. Before we end this video, let us check the key concepts that Teacher Jackie and I presented to you.
In this video, using a charged plastic ruler, you were able to determine the polarity of water, ethanol, baby oil, and cooking oil. Both water and ethanol are polar liquids, while baby oil and cooking oil are non-polar liquids. Through your self-learning module in chemistry in this video, we hope that you were able to learn more about molecular polarity and at the same time further develop your science inquiry skills, like in observing, inferring, and developing explanations based on evidence. Again, this is Teacher Jackie.
And this is Teacher Dan. Thank you for watching and see you in our next chemistry video.